I welcome you to another series of online lectures, and we're still looking at the atomic structure. So now what we get is that you look at the characteristics of an electron with respect it to the nature of light. So now what you get is that when you talk about light, light is just basically radiant energy. So the electromagnetic spectrum may include different types of radiation, meaning it ranges from radio wave until basically X-ray. So what you get is that we'll look at an electron, then you understand that an electron in an energy level is characterized by energy. Then it also behaves as a wave according to wave model. So if an electron is behaving as a wave, what you're talking about now is that you begin to talk about the radiant energy, and you also have to look at the properties of light. So what you get is that all forms of light travels in a wave. So light travels in a wave. So now the most important thing that we can look at are basically the characteristics of a wave. So there are some definitions that we need to understand. For example, if you talk about the wavelength, which is the symbol is lambda, is just a distance between two successive peaks. I'll show you as we get that. Then you have a frequency. A frequency is just a number of waves passing through a particular point per second or in 1 second. Then you have the amplitude. The amplitude is just the height from the base to the peak maxima. I'll show you what an amplitude when you look at the slide. Then you have velocity. Velocity is a distance traveled by wave in 1 second, and it is represented by c. So the velocity of light, which is also normally called as the speed of light, is just basically c is equals to 3 times 10 to the power 10 centimeters per second, or 3 times 10 to the power 8 meters per second. So if you draw a wave, it is something that looks like this. So you have the peaks here. So when you're talking about the wavelength is just basically you have a peak here, and basically you have the maximum peak. So the distance between A to B is what you normally refer to as a wavelength. Then what you get is that a wavelength is just one complete cycle. So if you get half of this, you draw half of that. Then you get quarter of this, which is a quarter. It comes here. So you have A, B, and C. So you have something like this. So this is A, then you have B, then you have C. So basically, when you're talking about the wavelength, it's just one complete cycle. If you are to stretch it, or if you are to represent it in form of a circle, it will look like this. But if you stretch it in form of a wave, this is how it will look like. So the distance between this point to this point is what you normally refer to as the wavelength. So it's the same thing. The distance between this point to this point is what you normally refer to as the wavelength. So the wavelength is just basically one complete cycle. Then you have a base to the maxima is what you normally refer to as an amplitude. So the distance between the base, where there's a dotted line here, to the amplitude here is what you refer to as the amplitude. So now what you get is that the determination of wavelength or frequency of this radiation is done by a spectrometer, and the results are presented in form of a chart normally called as electromagnetic spectrum. So this is what you have as electromagnetic spectrum. Then electromagnetic spectrum has like different region. There's a radio wave, there's a microwave, there's an infrared, there's a visible region. A visible region, this is what we're able to differentiate colors. Then you have the ultraviolet, then you have the X-ray, then you have the gamma rays. Then as you can see, the wavelength of a radio wave is quite longer, and the wavelength of a gamma ray is quite shorter. Then when the wavelength is shorter, the frequency is normally high, and when the wavelength is longer, the frequency is normally low. So what you get also is that energy increase in that direction. So longer wavelength have lower energy, and shorter wavelength have basically higher energy. So looking at the characteristics of light, so what you have is that the speed of light is just basically the product of wavelength times the velocity. So the speed of light, which is given by 3 times 10 to the power minus 8 per second, is just a product of wavelength in meters and frequency in per second. So this is what you basically get. Then you have Planck's quantum theory. Now, Planck investigated a black body radiation, and what he observed that the black body radiation is emission of light from a hot object. So from what you get from here, he proposed that light can be absorbed or released from atoms in certain amounts, and those certain amounts are normally called as quanta. So according to Planck's theory, light can be absorbed or emitted or released in certain amounts called as a quanta. So now what you get is that a quantum is the smallest part of energy that can be emitted or absorbed as the electromagnetic radiation. So meaning what you have is that energy is just emitted or absorbed in form of electromagnetic radiation, meaning you begin to talk about characteristics of the wave. So according to Planck's theory, he says that energy is directly proportional to frequency. So if you put in a mathematical operator, what you get is that E will be equals to HV, where H is normally called as the Planck's constant, which is 6.626 times 10 to the power minus 34 joules per second. So one key factor that we get from the Planck's theory is that energy is in certain amount called a quantum, or a smallest amount of energy that can be absorbed, emitted, or absorbed. It's in form of electromagnetic radiation. So what you get that energy is basically direct proportion to frequency, which is given by that relationship. So meaning when the frequency is high, the energy is also high. Okay, thus any body emits or absorbs radiation in one part, which is normally called as a quantum. Then two packets, it's called two quanta, and the list goes on and on. So to the previous equation, you can introduce a parameter n just to quantify how many quantas are there. So basically, n will just indicate the number of quantas that are given there. For example, the wavelength of a laser pointer is reported to be 663 nanometers. What is the frequency of this light? Remember from the equation, we know that the speed of light is just basically the product of lambda times the frequency. Now, our equation requires us to find the frequency. So what we do is we make frequency the subject of the formula. So to do that is that we multiply both sides by 1 divided by lambda, 1 divided by lambda. So this and this will cancel. So what you get is that frequency will be equal to c times 1 divided by lambda, which is just basically c divided by lambda. And this is our equation that we get there. Now note, c is the speed of light. So it will always be given as a constant, which is c is equal to 3 times 10 to the power 8 meters per second. So now one thing that you need to note is that for us to be able to solve this equation, note that the wavelength is given in nanometers and the speed of light is in meters per second. So we need to convert the nanometers to meters, and you know the relationship that exists between a nanometer and a meter is that 1 nanometer is equals to 1 times 10 to the power minus 9 meters. So in short, if you have 603 nanometers, this would be equals to 663 times 1 times 10 to the power minus 9 meters, which is just basically equals to 6.63 times 10 to the power minus 7 meters as your answer. So you substitute into the equation. So from the equation that has been given, what you get is that is equals to divide by lambda. Then you know 3 times 10 to the power 8 meters per second divided by 6.63 times 10 to the power minus 7 meters. So meters will cancel and your answer will be given in per second. So now I always advise people, for simplicity's sake, you can actually use simpler numbers where you can say 3 divided by 6 times 10 to the power 8 minus 7 per second. This will actually equate to 0.52, sorry, to be 0.452 times 10 to the power 15 per second, which is just basically equals to 4.52 times 10 to the power 14 per second as your final answer. Now note that all ours, this is expressed to two decimal places, this is to two decimal places, so our answer will also be to two decimal places. Let's move to another example. The frequency of violet light is 7.3 times 10 to the power 14 per second. Calculate the wavelength. So you still use the same equation. You know from our previous equation, you know that the speed of light is just basically the product of lambda times frequency. So from this equation, we've been given the frequency, and what we are calculating is basically the wavelength. So we make the wavelength the subject of the formula, meaning the wavelength will be equals to c divided by that. Then you substitute in the equation, you know that wavelength will be equals to c divided by that. This is equals to 3 times 10 to the power 8 meters per second divided by 7.31 times 10 to the power 14 per second. So the per second will cancel. Then you can now express into a simpler version or simpler form, which is 3 divided by 7.3 times 10 to the power 8 minus 14 meters. This basically will be equals to 0.410 times 10 to the power minus 6 meters, which is equals to 4.10 times 10 to the power minus 7 meters, which is equivalent to 410 nanometers if you do the equations. Because if you were to convert this into nanometers, what you get is that you have 4.1 times 10 to the power minus 7. Then you know that 1 meter is equals to 1 times 10 to the power 9 nanometers. So this is in meters. So you just substitute in the equation. So you have 4.1 times 10 to the power minus 7, 1 times 10 to the power 9 meters. So what you get, this is going to be 4.10 times 10 to the power 2 meters, sorry, nanometers, which is just basically 410 nanometers as your final answer. One more example. The orange light given off by a sodium vapor lamp has a wavelength of 589 nanometers. What is the energy of a single quanta of this radiation? Also calculate the energy in kilojoules per mole. So there are two things that we have to calculate here. First, we have to calculate the energy of a single quanta. Then what we've been given is basically the wavelength. Then you know E is equals to HB. Then V is to C divided by lambda. This is basically from this. So you make V the substitute formula, this is what you get. So when you substitute for V in this equation, this is what you have. H is Planck's constant. C is the speed of light, it's also a constant. Then lambda has basically been given. So from here, what we have is that energy will be equals to Hc divided by lambda, which is equals to 6.63 times 10 to the power minus 34 joules second times 3 times 10 to the power 8 meters second divided by 5.89 times 10 to the power minus 7 meters. So the meter and the meter will cancel. The second and the per second and second will cancel. So your answer will be in joules. So for simplicity's sake, you can simplify this like this, where you say this is equals to 6.63 times 3 divided by 5.89 times 10 to the power minus 34 plus 8 minus 7. Then after you simplify this, you actually discover that your answer will be, let's see if I can, so what we have, if we are to express this in a simpler form, this will be equals to 6.63 times 3 divided by 3.3 times 10 to the power 34 plus 8 minus 7 joules. So what you have here is that you have 34 plus 15. This gives you minus 19. So your answer, this equals to minus 19. And this is the 19 that you get here. So when you simplify, your answer will be 3.3 times 10 to the power minus 19 joules. And this is the joule per atom. That's a single quanta. So meaning it's energy that is released by one atom. So the second part, so we've calculated for a single quanta. Now we have to calculate the energy per mole. So now to calculate energy per mole, what we do is that you know that 1 mole is equals to the Avogadro's numbers of particles, which is 6.02 times 10 to the power 23 atoms. So now from the previous equation, we know that one atom will be equals to 3.38 times 10 to the power minus 19 joules. What about 6.62 times 10 to the power 23 atoms per mole equals to X? So you have one atom is equals to that. What about this number of atoms per mole? So now your answer will be X will be equals to 6.02 times 10 to the power 23 times 3.38 times 10 to the power minus 19 joules divided by 1 atom. Now remember the units of these are atoms per mole. So the atoms will cancel. What will remain as your answer is joule per mole. So when you simplify that, what you get is that you get your answers to be 203,476 joules per mole. Now note that the answer requires it to be in kilojoules per mole. So you know that 1 joule is equivalent to 0.001 kilojoules. So you just substitute into this value here. So you have 203,476 joules per mole, which is just basically equals to 203,476 0.001 kilojoules per mole, which is just equals to 234.476 kilojoules per mole as your final answer. Okay, with this lecture series, what I'll do is that I'll end from here and I'll see you into the next series. Thank you very much.